Okay, so thanks very much. Can you see my screen? Yeah. Okay, great. Right. First, I'd like to thank Elio and Thomas for putting together this a very interesting workshop and giving me the opportunity to speak here. I've had the privilege to work with these great people listed here. I'll highlight them as I go along. What I'd like to suggest is that this is not a very long talk, but if you have a short clarification question, I suggest that you would just unmute and ask it. I'd rather not lose you. Right, so with that, let me jump in. So I'm going to talk about moire materials. I guess in a sense, this is a multi-orbital session, so these are very, very multi-orbital systems. You'll hear about them more, I think, tomorrow by Matthias. But just as a very, very brief introduction, so one thing that we'd like to do in studying emergent phenomena in condensed matter system is to enhance the role of interactions. And one way to achieve that is to create flat bands. And in this context, I'd like to just stress that moire materials, in some sense, are a class of their own in this a variety of flat band systems. So we know of various ways to create flat bands. One is just to put electrons in a very, very deep lattice that quenches the kinetic energy. And this happens in many correlated materials and with D and F shells. And we know that you tend to get Mott insulators, for instance. A very different class is just take a 2D electron gas and apply a large magnetic field. So this is another way of creating a flat band. As we know, what you get is Landau levels, which are very flat. These are essentially just new kinds of bands. And these have very interesting properties. And they're also flat, but they're kind of different from Mott insulators. As we know, the single particle wave functions are actually extended. They have a topological character, but you really need to apply this very large magnetic field to see this physics. And the new class of materials are these moire materials, for instance, a magic angle graphene. So here you create the flat bands by a very subtle interference effect of the tunneling of electrons between these two layers. And if you tune the angle, the twist angle just right, as we've learned, you can get these extremely flat bands. Okay, so it's not the entire band structure that becomes flat. It's only these narrow bands in the middle. Now, as I'll stress again and again in this talk, these bands are also actually topological. So they share some features with the wave functions of Landau levels. On the other hand, they don't require any magnetic field. So this opens a whole new a window of possibilities. And as we know, in this spectacular progress that has been made over the last a couple of years, when you partially fill these bands, you get various new phenomena like correlated insulators, Chern insulators, superconductivity, and so forth. Okay, so this is what I'm going to discuss. I'm going to focus on a particular problem inspired at least by magic angle graphene, which is the fate of the system at charge neutrality, which means that these narrow bands are exactly half filled. Okay, you don't add any external charge to the system, and I'm going to present two studies. The first one is asking a question of principle. So in this kind of system, even not getting into what the microscopic Hamiltonian, which is quite complicated. This is not an easy problem, but we just want to ask as a matter of principle, what could happen at charge neutrality? Okay, and the one input we want to build in is the topological character of this band. So we want to know what constraints does the topology of the bands impose on the nature of the ground state at charge neutrality. Okay, so for instance, we'd like to know, can the system become insulating without breaking any symmetry, for instance. We know that by breaking symmetry, it can become insulating. In the second part, I'm going to be a little bit more ambitious maybe, and I'm going to ask, well, what actually does happen at charge neutrality? And for that, we'll have to resort to numerics. And I'll show that in fact the kind of standard Hamiltonian that we believe describes a magic angle graphene at charge neutrality actually doesn't suffer from the sign problem in quantum Monte Carlo. This comes about because of a symmetry that I'll describe, and I'll show some first results for this problem. Okay, and I think there are many other interesting things that can be studied using this technique. This is just in the beginning. Okay, so that's my my outline. Topology is gonna recur in this talk in many times. So first I'd like to describe what's actually topological about the bands of magic angle graphene. It turns out that there's a particularly interesting and subtle form of a band topology that appears. Okay, so here again is a calculation of the band structure from the Bistritzer-McDonald model of twisted bilayer graphene. Here are the two narrow bands, and there are other much more broad bands. Okay, so these bands become extremely narrow, close to the magic angle. Now here's just a blow up, just a zoom in of these two narrow bands. Okay, so it's the same bands, just with a bigger scale. And you notice that these two bands, the valence band and the conduction band, actually touch each other at two Dirac points. And whenever you see band touching at Dirac points, you should in 2 dimensions, you should always ask, what's the symmetry that protects these Dirac points? What actually prevents a gap from opening at these points? And in this case, the Dirac points are protected by a particular symmetry. So they're protected by the product of a 100-degree rotation around the z-axis and time reversal. In fact, this is the same symmetry that protects the Dirac points in regular graphene. Okay, this is what prevents a gap from opening. For instance, you know that if you turn on a sublattice potential, that breaks this combined symmetry because it breaks C2 and that opens a gap. Okay, so this just looks like a miniature version of graphene, if you like, but it turns out that there is something special about this pair of Dirac points. Okay, so when you have a Dirac point which is protected by this so-called C2T symmetry, you can define a chirality or a winding number for each one of these Dirac points. And usually you're used to thinking that over the entire Brillouin zone, the net chirality or net vorticity, each Dirac point is like a vortex. The net vorticity of these Dirac points over the entire Brillouin zone has to sum up to 0. Okay, but in this case, in the flat bands of moire of magic angle graphene, it turns out that these two Dirac points actually have the same winding number. So that's kind of anomalous. That's unusual. Okay, and it's actually not hard to understand where this property is coming from. Okay, if you think about how these two Dirac points form, they actually are descendants of the two Dirac points of the original two graphene sheets, which are twisted by a small angle relative to each other. Okay, but they came from the Dirac points of graphene of the two layers of graphene from the same valley, and this is actually why they inherit the winding number from the two Dirac points of a graphene from the same valley, and that's why they have the same winding number. Okay, so the fact that the winding number is the same tells you that there's something anomalous or topological about these bands, and this goes under the name of fragile topology. So let me just briefly explain what that is. Okay, so this is a new kind of symmetry-protected band topology. In this case, it's protected by C2T symmetry. To explain what it is, I'll use a toy model, not the original twisted bilayer graphene. Okay, but what the model is not so important. It's a 4-band model. There are 2 orbitals per unit cell, and therefore 2 Pauli matrices, sigma and tau. Okay, they're not related to value or spin, just two orbitals. Okay, the exact Hamiltonian is not so important. What is important is that it's invariant under this combined C2T symmetry. Okay, and a C2T symmetry is an anti-unitary symmetry. So this is complex conjugation over here, and times some unitary operator. The important thing to note about C2T is that it maps momentum to itself, not to minus itself. Okay, because T flips momentum and C2 flips it back in 2D. Okay, now if you diagonalize this Hamiltonian, you find the 4 bands, and each pair of bands touch each other at 2 Dirac points. Okay, and it turns out that each pair of these Dirac points actually have the same winding number. So we would say that each pair of bands, both the lower and upper bands, have this property that they have fragile topology. And what does that actually mean? Okay, so let's say we focus on the lower bands over here. Okay, so these are two bands. We can span them in terms of a smooth basis over almost the entire Brillouin zone by two wave functions. Now, in a proper gate choice, okay, the C2T acting on this pair of bands would actually just look like complex conjugation. So we can represent the two states that are spanning this pair of bands by two real vectors. And therefore, the effective Hamiltonian projected to these two bands would be a real 2 by 2 Hamiltonian. So it just has two Pauli matrices, eta z and eta x, but no eta y. Okay, so the eta y is forbidden by symmetry. And therefore, you see that we can define this angle theta k and ask about the winding of this angle around the Dirac points. So this is what this angle theta k is doing over the entire Brillouin zone. And if you work it out carefully, you'll see that these two Dirac points actually have the same winding number. So this means that these two bands have fragile topology. Now, the consequence of this is that unlike what we're used to, when you change parameters of the Hamiltonian, you can move these Dirac points around, but even if they collide, they actually cannot annihilate each other. Okay, so the fact that they have the same winding number means that this band touching of the conduction in the valence band is actually protected, and even if they collide, they would just form a quadratic band touching with a total winding number of 2, but they can't gap each other out. Okay, the only way to gap to separate these two bands by a gap is either to break C2T symmetry, okay, so which is the protecting symmetry, or to break a different symmetry. For instance, it turns out that breaking translational symmetry would also do the trick. Or if the two lower bands mix with the upper bands, you can actually separate all four bands from each other without breaking any symmetry. Okay, so the protection is really tied to having two isolated bands. This is what's fragile in fragile topology. Okay, so that's fragile topology. Now, what does that have to do with experiments? Okay, so what's the consequence of this for, say, for the gap, for the possibility of a gap at charge neutrality in magic angle graphene? Okay, so there's a very simple consequence. The two narrow bands of magic angle graphene have fragile topology. So this means that as long as the system is at the charge neutrality point, and if the active bands are separated from the rest of the spectrum by a gap, which they are, okay, so the two narrow bands are separated from the more dispersive bands, then the system actually has to be metallic or semi-metallic as long as we don't break a symmetry. Okay, so for instance, if we break C2T symmetry either explicitly or spontaneously, we can separate them by a gap, but otherwise the system has to be metallic. Okay, now there are other symmetries you can break. For instance, if a translational symmetry is broken, that's like adding more bands. And this would also allow opening a gap. Now, a corollary of this statement, right? So this is a statement about non-interacting Hamiltonians, but an immediate consequence of this is that at the mean field level, as long as we can describe our system using some mean field single particle Hamiltonian, we cannot open a gap at charge neutrality unless we break a symmetry or mix in the higher bands. Okay. Now, what happens in experiments? So the answer is mixed. Okay, there are some experiments that show that at charge neutrality the system is a semi-metal, and other experiments that show a gap. Okay, so this is an example of an experiment from Dmitry Efetov's group, and this is the resistance as a function of filling. Okay, look here, this is the filling fraction of the system. This is charge neutrality, and here the resistance is very high and also shows activated behavior. So it looks like, at least for this sample, there is a gap opening at the charge neutrality point. And the question is, what does that mean? So does that mean that the system breaks a symmetry spontaneously? Does that mean that that symmetry is not there, is explicitly broken by the setup, maybe by the substrate, or is there another possibility? Okay, so there are many theory proposals for different spontaneous symmetry broken states that might appear here. But the question I'd like to ask is slightly different. Suppose we turn on some strong interactions, but these interactions are still acting essentially only within the flat band. So the rest of the spectrum is separated by a large gap. Okay, so can we get a gap even without any symmetry breaking? And do we have to have a topologically ordered state, or can we get a so-called featureless insulator? Okay, or in other words, what constraints does the topology impose on the possibility of gap opening? Okay, so the answer, it turns out, is that the topology is actually does not obstruct opening of a gap, of a featureless gap without breaking any symmetry. And I'd like to demonstrate that, okay, using a simple model. So suppose I have a pair of fragile topological bands, like in the model I've showed, and I tune the system such that the two Dirac points merge into this quadratic band touching with a winding number of 2. Okay, so the system initially is in a semi-metallic state. The Fermi level is here. Okay, and now I want to turn on strong interactions. Okay, now for this construction, let me imagine that in the conduction band, there are these two electron valleys, okay, which are away from the Fermi energy, and in the valence band, there's one hole valley. Okay, and what can happen? I turn on an interaction of this form between the electron valleys and the hole valley. So this is a repulsive interaction, so it's an attraction between electrons and holes. And what this interaction can form is a bound state, okay, made out of electrons from the three valleys. It's a bound state of two electrons, E1, E2, and one hole, H. Okay, so it's a bound state which is a fermion, and it's a fermion with charge 1 because it's two electrons in one hole. So this is a so-called trion. So such excitations actually exist in semiconductors. Okay, so this is our bound state, and we can arrange our model such that the lowest energy of this trion bound state occurs at the gamma point. So essentially, what we've done is we've created a new band of these composite objects, which occurs at the gamma point. Okay, now once we do that, we can turn on another quartic interaction, which hybridizes psi, which is electrons near gamma, with the trions. And since the trion has the same quantum numbers of an electron, it can simply hybridize with the original electron. Okay, so using that, we can show that without breaking any symmetry, a gap can actually open. Okay, or slightly more explicitly, we can describe the system at low energies by close to the gamma point by this 3x3 real Hamiltonian. It has to be real because of C2T symmetry. The 2x2 block describes the quadratic band touching of the original electrons, and this last row is the trions, and the trions can hybridize by interactions with the original electrons, and you get a gapped spectrum. So you've basically separated the lower band from the other two. The Fermi level, because you're at charge neutrality, is right in this gap. Okay, and you've done this without breaking any symmetry and without forming topological order. So this is actually a featureless insulator. Okay, so this is a picture of what the wave function looks like. That you can represent the wave function as a three-component real vector. The z component of this vector is the trion component. So you see that far away, this is the wave function of the lower band. Far away from the quadratic band touching, you actually haven't done anything. This vector is in the plane, and it has a winding number of 2. And only close to the gamma point, it has a strong trion character. Okay, so this is a proof of principle. Of course, we don't know if this actually happens in any actual system, but it just shows that in principle, you could get a gap in separating fragile bands just by interactions without breaking any symmetry. Okay, so that's part number 1. Let's skip this. I'm probably doing not great with time. How am I doing with time?
Yes, so we started nearly 10 minutes late, and we're so I was planning 10 minutes in total more, including the questions.
10 minutes more,
including questions.
Okay, so I'll be a little bit brief here, and
thank you.
Hopefully you have more questions about this part, you can meet me in the Wonderby. Okay, so now I'm going to try to answer a more practical question: what actually happens at charge neutrality? Okay, and for that we'll need to do some simulation. So let me describe what simulations are out there in the market. Okay, so here are again the bands of magic angle graphene. Okay, and the system is very complicated. The first thing that we'd like to do is to basically project our problem to these narrow bands. The Fermi level at charge neutrality is right here between the blue and the red band. So we'd like to project out all the remote bands and write down an effective Hamiltonian that lives only in these low energy degrees of freedom. Now, there's several factors that make simulating the system pretty challenging. Okay, the first one is precisely this topological character of these bands. Okay, so unlike what we're maybe used to from correlated materials, we can't write down a localized one-year description of these bands. There's an obstruction which comes from the topological character of the bands. Okay, if we try to write down one-year functions, they would have power law tails. So there's no sort of easy local Hamiltonian, just like in a Landau level. The other difficulty is that there are many, many degrees of freedom still. Even if we project the other bands, there are two narrow bands and two valleys and two spins, and all of them are very strongly interacting together. So total eight orbitals, if you like, per unit cell. And that's of course very heavy numerically. Okay, and they're long-range Coulomb interactions. So we definitely know that long-range Coulomb interactions are important. Okay, now for at least for t equals 0, people did some exact angulization and some DMRG studies, and each of these have clearly their own limitations. Okay, what we'd like to propose is at charge neutrality, we can actually apply a quantum Monte Carlo, okay, which is not restricted to sort of quasi one-dimensional geometries, and also it works at finite temperatures. And we'll apply it directly in momentum space, such that we avoid the need to write a localized basis in real space, which we cannot really do due to the band topology. And at charge neutrality, I'll argue that the system has an approximate particle-Hall symmetry that prevents the sign problem. Okay, so I really won't go into a lot of details here. I'll just highlight the main points. Okay, so at charge neutrality, magic angle graphene seems to have at least an approximate particle symmetry. So this is again this experimental plot of the resistance as a function of density. And with a little bit of loving eye, okay, around density 0, which is charge neutrality, most of the features are kind of symmetric, left and right. Okay, so what causes this approximate particle-Hall symmetry? Well, you can say it's just inherited from the approximate particle-Hall symmetry of graphene. This is again the calculation of the narrow bands, and you see that the spectrum is indeed E2 minus E symmetric, but in a very peculiar way. Okay, the solid lines here are the bands at valley k, and the dashed lines are the bands at valley k prime. And you see that for each energy of the band at valley k, there's a state at minus the energy at k prime. So there is an approximate particle-Hall symmetry, but this particle-Hall symmetry actually flips valleys as well. Okay, so here's the standard model that people have been using to try to describe the physics of magic angle graphene. Okay, so there's a single particle Hamiltonian, which is the Bissricher-McDonald Hamiltonian plus Coulomb interactions. Okay, and in the microscopic Hamiltonian, there are actually 4 degrees of freedom, which are sublattice A and B, layer, spin, and valley. Okay, so the single particle Hamiltonian is a 16 by 16 Hamiltonian. Okay, so a single particle part of the Hamiltonian has a part which is just 2 sheets of isolated graphene twisted relative to each other. These are these unitary operators. They rotate the Dirac matrices by theta and minus theta, the 2 layers. Okay, and the HT is the tunneling Hamiltonian between the layers. I won't describe that in detail. Okay, but so this Hamiltonian is actually not particle Hall symmetric, but it nearly is. Okay, and this is maybe the most crucial point. Okay, there is naturally a small parameter here, which is theta. Okay, so at the magic angle. Okay, sorry, this Hamiltonian. The tunneling has two parts, which is interlayer intrasublattice and interlayer intersublattice. Okay, so this parameter theta at the magic angle is 1.1 degrees. Okay, so this is a 2% effect. Okay, so what we're going to do as a first step, we're going to neglect these unitary matrices, just replace them by one. And it turns out that once you do that, the system actually has a particle Hall symmetry. Okay, so I won't show this in detail, but the statement is this: the full Hamiltonian, including the interaction, once you do the small angle approximation, you neglect the angle theta, has an approximate anti-unitary particle Hall symmetry, which is it's an anti-unitary symmetry, and it transforms C dagger into C, flipping the valley, the sublattice, and the layer. Okay, so it's a quite complex operator, but this is the thing that works. Okay, and why is this useful? So it turns out that this kind of particle Hall symmetry is exactly what you need in order to prevent the sign problem in quantum Monte Carlo. Okay, so it's well known for practitioners that if you have such a many-body anti-unitary particle Hall symmetry and a U1 symmetry, which in our case would be either valley or spin conservation, then you don't have a sign problem in quantum Monte Carlo. Okay, technically you do a Hubbard-Satonovich transformation, you have Hubbard-Satonovich fields, and for every space-time configuration of these fields, in our case, these fields are in momentum space, you can show that this weight, this effective Boltzmann weight, is actually non-negative. Okay, it's real and non-negative, and I won't show the details. Okay, but it turns out that this method can be generalized to various perturbations, so it allows for a spin polarized system at charge neutrality, so you fill really only one out of the four orbitals. You can apply a Zeeman field or a orbital magnetic field or perpendicular electric field, and so forth. Okay, there are various perturbations you can add, physical perturbations you can add to this Hamiltonian, which won't spoil this property. Okay, but of course, doping, going away from charge neutrality, unfortunately, would cause a sign problem. So we focus on charge neutrality here. So just in 1 minute, I really won't show any details because I'm out of time. Okay, so I'll skip this. Apologies for that. Okay, let me just flash a few results. Okay, just as a teaser, and we can discuss it later. Okay, so it turns out that the results are very sensitive to the single particle bandwidth, and we don't quite know what that single particle bandwidth is. It's very sensitive to the angle, how far you are from magic angle. But I'll just show results for two parameter sets. Okay, the first is for a single particle bandwidth of 8 millivolts. Okay, so it's a pretty narrow band. And it turns out that here our simulations show very clearly that the ground state is an insulator. There is a gap opening due to symmetry breaking. And the symmetry breaking is this what's so-called intervalley Kramer's state, okay, or KIVC. It's microscopically, it's a state where there are spontaneous currents around the unit cell, which are staggered. Okay, this is the moire unit cell. This is the original graphene. And I really won't show any details. Sorry for that. Let me just point out there's one feature which is interesting. The gap actually opens at the temperature which is way, way above the temperature where the order sits in. Okay, so there are apparently many local fluctuations. This is a little bit like a pseudo gap. So there's a big gap that's opening even before the system actually orders. So that's for a bandwidth of 8 millivolts. When you increase the bandwidth to 14 millivolts, the system is actually a semi-metal. Okay, so we call it a correlated semi-metal. There's still signatures of strong correlations in this state. But interestingly, if you do a Hartree-Fock calculation for the same parameters, this would actually predict still like an insulating KIVC state with a huge gap. Okay, so Hartree-Fock really exaggerates the tendency towards ordering, as you might expect. Okay, so I'll skip the details here and just flash my conclusions. And thank you very much for your attention. Sorry for going over time.